Hello forensic chemists. Today's video is going to be on gunshot residue, and let's get started. And so whenever we're dealing with gunshot residue, we need to learn a little bit about what goes into ammunition. This is a typical construction of ammunition here. We have a cartridge. It could be brass or nickel. Most common is brass. It could be rimmed or rimless. This has a rim on it right here. Okay, so that's called the rim. This is the little slot for the primer, and the primer is right here. It's a little button that goes inside this spot right there. The primer has a contact or shock sensitive explosive, which we will discuss in a little bit. We saw it in the explosives video, though. It was lead stiffnate, but it also has an oxidizer, barium nitrate, and some antimony sulfide. And then you have the grains of propellant. This is gunpowder, and so that fills up the inside of the cartridge, and then the bullet is just press fit inside the cartridge. So the bullet goes right here. Okay, so that's pretty bad. But anyway, this is an example of a bullet. It's been cut in half, so all of these have been cut in half. And you can see that this has a copper jacket around the outside, and then it's filled with lead. And this has a hollow indentation in it. This is what we call a hollow point projectile. This is made upon impact to open up. Sometimes there'll be 5 little cuts in the front edge of this, and those cause a ripping effect. As this hits fleshy material, it will expand and create maximal damage. And so when we talk about a full metal jacket, you may have heard of that, popular Vietnam movie. That's when the jacket goes all the way around the front of the bullet. So full metal jacket is not a hollow point. A hollow point has this hole in the front where it's been hollowed out. A recent invention, I guess, maybe in the last 10 years or so, with airline security, they came up with other kinds of munitions, because if you think about the air marshals, the particular tasks that they have at hand, if there's an active shooter on board of an airplane and they want to take them out with a weapon, they don't want to puncture the skin of the aircraft, because this could cause other problems with the aircraft and its airworthiness. And so you might see other types of ammunition. This is one example where instead of a straight hollow point, they have a plastic bead in here. And so that plastic bead pushes down inside the projectile when it hits fleshy material, and it stops the bullet, but it also causes the bullet to impact and deposit all of its energy inside the body. The interesting thing about those, like I said, the bullet is almost guaranteed not to go through a body. It's supposed to deposit all of its energy in the body, and so this would allow an air marshal to shoot someone and not worry about the bullet going through that person and injuring a person behind that person. The gunpowder is not just black powder, sulfur, and potassium nitrate. It's actually a more complicated formulation now. If you were to look at these powder grains under a microscope, you would see that they're extruded. Looks like an extrusion, tiny little cylinders of propellant. And so if you're looking under a microscope, you'd see these little cylinders of propellant. And it was a slurry, and it was pressed through a little screen, and they make highly calibrated little powders that burn at a given rate. And so this is another physical property of black powder that or gunpowder that you could see. So micrographs of different kinds of black powders would potentially look different. And so some of the constituents that are of forensic interest are the primer elements. And so this is the main, these are the main chemicals, these atomic, these various atomic signatures are in the primer. And so we have a primary explosive that's shock sensitive. And so when the firing pin strikes the primer, it causes the lead stiffenate to detonate. This releases the oxygen from the barium nitrate, and then that oxygen can go to antimony, which is in a reduced form, antimony sulfide. So the nitrate, the oxygen will burn the antimony and create powdered residues that are lead oxide, barium oxide, and antimony oxide. And so these would be the three these are the three elements that you would look for to ID gunshot residue. Now, with all explosive or propellant burning, you never have 100% burn. And so you will have some nitrocellulose left over, maybe even traces of nitroglycerin. You might have stabilizers. So these, we'll see, these stabilizers are added to the black powder to give it a long shelf life. And so you might see diphenylamine, ethyl centralite or methyl centralite, hydroquinone or resorcinol. And then you might have a vigorously burning compound like dinitrotoluene that will essentially cause the propellant to burn a little faster and reduce the flash that comes out of the muzzle. So if the propellant is still burning as it leaves the muzzle, you'll have a large flash. But if you have something that will enhance the burning, then the burning occurs inside the barrel before the bullet exits, and that would be a flash suppressor. And then these grains, like I said, they're engineered grains to burn at a certain rate, and you don't want any kind of jarring or whatever to cause those grains to break up. And so this plasticizer may be added to some formulations to keep those grains a little bit flexible and not brittle. So some of these explosive formulations might have a little bit of polymer binder in there just to make sure that they stay together and don't break up into smaller particles. A smaller particle would burn faster, and so if you wanted a repeatable ammunition, you would want to have more of a plastic formulated gunpowder. So here's an example of a revolver being fired. And so you can see the cloud here, and you can see that the gunshot residue is going to be deposited on the forearms here, and most definitely in the thumb area. So this is the strongest concentration of gunshot residue. You can see this whole cloud. And this is right after the bullet exited the weapon. And so this cloud contains that lead, antimony, barium, traces of nitrocellulose, maybe some of the plasticizer if it wasn't burned up, and so on. So we can track those trace elements on the shooter. But if there's also a person standing nearby, let's see if I can do this. They're going to, anybody near this person, this cloud is going to drift over onto them. And so they will also test to see if a person was nearby the shooter. So you can't necessarily tell whether the person fired the firearm or was just in the vicinity of a firearm. And if this were inside a vehicle, everybody in the vehicle would have gunshot residue on them because the vehicle's enclosed and this cloud would fill the whole vehicle. So we would collect that gunshot residue here on the hands, most in particular. And this photo was given to me by a high school friend of mine. She was posting pictures of her practicing with her handgun, and I said, that's a great photo because of the cloud, and so I asked her if I could use it in my class. So here's a nicer image of the bullet actually exiting the gun, and you can see the hot particles of metal coming out and how they fly around. Also, you can see how much flame comes out in a revolver and goes back towards the shooter. I mean, the finger is down here on the trigger, so the finger is just right here in this area, just behind this revolver area. And so you're going to get some hot gases landing on the fingers. This is going to burn and go up. It's going to go up and blow back onto the shooter. And then these hot particles that are shooting out here, these are the little bits of GSR, gunshot residue. You can actually see this looks like a full metal jacket projectile here. Coming out of that revolver. And so we would do GSR in two particular cases or types of cases. We would look at the bullet entrance into the victim to estimate the firing distance. And then we could also sample GSR on hands or objects to determine whether or not that person has discharged a firearm or whether they were in the presence of a discharged firearm. So mostly we would do the back of the hand. They're doing the palm here, but certainly you would want to get the top ridge of the hand and the back of the thumb. Occasionally you might sample the face, the hair, or clothing, but most of the time it's the hands that are sampled. Okay, so this would be a close range entrance wound, and you know it's close range because you still have charring. And so the gases, the propellant was still burning when it hit the jacket. If it's farther away, you won't see charring, but you would have to test for little bits of gunshot residue. So you might see little pits of the gunshot residue. And we'll see that in a future slide here. So these color tests for the gunshot residue, these are presumptive tests. We have the modified grease test and the sodium rhodizonate test. The grease test tests for nitrites, and then the rhodizonate test tests for lead and barium, in particular lead though. And then if you were to take that swab of the clothing and so on, you could send it off for analysis using SEM, scanning electron microscopy, and then other techniques are also available for atomic composition. So this is the procedure for the modified grease test. And so you need desensitized photographic paper and these solutions here, and this would all come in a kit. Okay. And so then you put the evidence item question side down on the gelatin coated side of the treated paper, and then you soak the acetic acid cheesecloth on the question item and press with a hot iron. And so this transfers the gunshot residue over onto the photographic paper and creates a reaction that it shows indicates the presence of nitrite residues. And so here's that photographic paper that is showing the color change related to the nitrites. If you want to test for lead in the gunshot residue, here's the procedure for the sodium rhodizonate test. And so here you will get a pink color, and then you could spray it with hydrochloric acid and get a purple color. And so the rhodizonate test is the pink color of the sodium rhodizonate. Here is an entrance wound, and you see the particles that had impinged onto the clothing, and you see that the lead residue is showing a pink color. Here's some pictures from a former student, Joe Trevino. He gave a talk on gunshot residue last year. This year we had the good fortune of him coming to talk on times when he's used alternate light source detection. So Joe works for the police department up in Garland, Texas. He graduated from SAM with his forensic chemistry degree in 2013, and then went up to Manhattan at Pace University and got his master's in forensic science, and then got a job back here with the Garland PD. And so in terms of looking at clothing, he says this is almost always the case. It's the muzzle to target determination. And so they're looking at the spread of the gunshot residue to determine how far away the target was when the firearm was fired. And so then the sodium rhodizonate test, this is what we just saw here. The rhodizonate buffer sprays makes it pink, and then you can spray on some hydrochloric acid and it changes that pink color to a blue-violet color. Now, again, you can take images, photographs of the entrance area. You can, snip pieces off and extract it or send it off for analysis. And so these are almost always done for the distance determination to see how far away the firearm was from the victim. Now, in terms of suspects' hands and clothes, there's a couple of different ways. You have swabs and tapes. I've got a couple of images of swabs here. So here's a cotton swab that you would swab on the hands and then pull it down inside the cup. One second. And so then these are nice little swabs. So you pull the swab back into this little protective cup and close the lid and then snap off the stick. And then you can label it and send it in. So this would be the analysis kit. You have the swabs inside those little plastic cups, and you've got some evidence tags, and you would bag that and send it in for analysis. Here's another way of doing it. These are little swabs that have a foam insert and a little cap that goes on it. And Penny is here just to show you the scale. And so here we have one labeled left and right for the two hands, and then security seal, and you've got date and time stamps and so on. So you would swab the person with the back, swab the back of their hand with this little foam swab, and then fill out the information, put the security seal on, and send it in for analysis. Now, some of the analysis can be quite high tech. That's why you have to send it in. It's very rare that you would have a scanning electron microscope at a police department or some sort of frontline investigative unit. But you would send this back to a DPS lab or some other kind of well-equipped lab to do the analysis. So scanning electron microscopy, these things can run $200,000 to $400,000 for the instrument. Here's the sample chamber. You've got some adjustment knobs to adjust the sample, to move it left and right, forwards and backwards, elevation to focus the beam. There's also, it's all electronically controlled inside the computer to focus the beam. And then you can shine the beam on a particular particle, and that will cause X-rays to come out of the particle. And those X-rays can travel up this tube, and they hit a crystal, and that crystal causes those X-rays to be dispersed. It's kind of like a monochromator. And so that's what we mean by energy dispersive X-ray. And the detector is up here in this liquid nitrogen door. And so the detector is kept very cold, surrounded by liquid nitrogen, and it keeps the background very low. And so you can shine the electron beam on a particle and analyze the X-rays that come out. And so here's the sample. Like I said, you have those knobs that adjust the tilt and angle and forwards and backwards of the sample. Then the tall tube and the electron microscope, these just different electrical coils that focus the electron beam, and it scans along the sample back and forth. And these backscatter electrons are detected, and that gives you the image. And then if you see a little particle there, you can shine that beam straight onto that particle and blast it with electrons, and then X-rays will come out. And then they enter the X-ray detector. Of course, they go in all directions, but you're just analyzing the ones that enter the detector. And so this electron beam, again, the electrons that are most easy to hit, you might think this is strange, the 1s electrons are closest to the nucleus. And so they take up a really small space, but that actually works to your advantage, because if you think about the 2s electrons, there's still just 2 electrons in the 2s shell, but they're spread out even further. So this would be the diameter that would contain the 2s electrons. This is the diameter that would contain the 2 1s electrons. And so they're much easier to hit with the electron beam. And so the electron beam comes through, it's very negative, and this electron is negative. And so it is scared away by the beam. And so this electron comes blasting out of the atom, leaving behind a hole that's very close to the nucleus. And so this electron jumps down and spits out an X-ray. Now the energy difference between these two orbitals is characteristic of the element. So this is a great way to get elemental analysis. You scan the image with a scanning electron microscope, and then when you find a suspected gunshot residue particle, you can aim the electron beam at that particle, and out will come characteristic X-rays of that particle. If it's a metal oxide, then you're going to get oxygen and whatever the identity of that metal is. So here's a particular scan out of the scanning electron microscope. This is an energy dispersive X-ray scan. And we see oxygen, which is indicative of the metal oxide. And we see lead. You see lead here. You've got mainly the 2s to 1s transition. And then you might have some peaks related to the 2p to 1s, and then maybe the 3s to 1s, and so on. So you have K, L, and M shells. And so you have these L to K jumps from the electrons. We have the same behavior in antimony. So here are the 3 peaks for antimony, and then here's barium. So we have the 3 or 4 peaks related to barium. So this would be a confirmation that this is a gunshot residue particle because it contains all 3, lead, antimony, and barium. When you're looking for gunshot residue too, just from the SEM image, you're looking for rounded particles as if they've been melted. So they look like they were molten at one time and then they cooled. You might even see some cavities. They're irregular shapes, and so you might see some irregular shapes here like this. That's not quite a sphere, so it looks irregular. This one's spherical, but it does look like it's been melted. This has got some bumps on it, and that's we'll see that may be misleading when you see those kind of bumps. It may not be gunshot residue. This one's definitely gunshot, or likely gunshot residue because of the irregular shape. It looks molten. It looks like it's been, cracked or crushed. And so then let's look at some of the particles that are the same size as gunshot residue, but would be definitely not gunshot residue. And that would be pollen grains. So pollen is roughly the same size as gunshot residue, but you see, even though they're round, they're definitely not molten, and they're not irregular in shape. They're complex in shape, but they're not irregular. And this is a very regular pattern. You see hexagonal ring structures. You see all these spikes. There's no way that this is a molten particle because those spikes would melt away first. Whenever you have a spiked object that has a high surface energy, and as soon as you heat that up, those spikes will either melt and shrink away, or if it's flammable and gets hot enough, those spikes will be the first things to start to smolder and burn because they have such a high surface energy. So you see all these different particles and all these different sizes. This is what causes my allergies to go berserk. They get in my nose and my eyes, and I definitely respond to these pollen grains. So these are going to be on our clothing, on our hands, and everything. And if we're testing for gunshot residue, we're definitely going to be detecting pollen. But there shouldn't be any lead in pollen, or antimony, or barium. Pollen is organic, and so it's going to be carbon, hydrogen, nitrogen, and oxygen. Maybe a little bit of sulfur. I mean, these are made up of proteins, and so it's going to be carbon, hydrogen, nitrogen, and oxygen. And so we were looking for these spheroidal or rounded, non-crystalline, irregular molten particles that are 1 to 10 micron in size that contain barium, lead, and antimony. If they only contain 2 of these components, then they're commonly described as associated with GSR, are characteristic of GSR, are consistent with, or indicative. But if you have all 3, then you can say it's confirmed to be gunshot residue. Now, gunshot residue can't determine whether the victim's death was a result of homicide or suicide because a person who dies from a gunshot wound was in the presence of a gun being fired. And so whether the person was firing at themselves or whether it was a homicide, you couldn't tell because the victim would have gunshot residue on them either way. In fact, nowadays GPS will not even run the sample. They want other kinds of evidence to decide between homicide or suicide. Gunshot residue is not helpful, so they don't waste their time in the lab running GSR for confirming a suicide. It's also understood that it can't tell the difference between a shooter and a bystander. And in fact, DPS will only run GSR kits involving crimes against persons now, just because they're busy. And so it has to be a homicide, attempted homicide, aggravated assault where a weapon was used, or questioned death investigation cases. And so if you get a positive GSR that's consistent with that person being in the vicinity of a fired weapon or having fired the weapon or even having touched an item with gunshot residue on it. So there's some suggestions that cases where the victim was tested after they had been in a police car, that evidence was not allowed because they touched the back seat and there might be gunshot residue in the back seat. So negative GSR just means that there was a lack of that exposure of the individual to GSR, or that they washed their hands, or it was removed in some other way, maybe weather conditions, or perhaps that ammunition lacked the lead, antimony, and the barium components. Or maybe the sample was heavily, like the hands were covered in mud, or some other kind of soil that disrupted the sampling. And sometimes the SEM EDX test failed, but the organic testing was positive. So they detected the other components like the ethyl centralite and maybe the nitrocellulose or nitroglycerin. Other kinds of false positives might be mishandling, or from previous shooting. You might have somebody who is had just returned from the firing range, and then they were involved in some sort of altercation where a gun was shot, but they didn't fire it. But yet there was a false positive because they had gunshot residue on their hands. It wasn't from the crime, it was from previous handling of a weapon. Or perhaps they work in construction and they use stud guns. So this is a way to drive nails into concrete. And so in construction, they have these little 22 blanks, and you load a blank in there, you put a nail inside this, and you hold it down onto the stud, and it drives the nail through the stud and into concrete. So if they work in construction and they handle stud guns, they may have some gunshot residue on their hands from these little 22 blanks. Now you can get false negatives. So a person fired the gun, but then the GSR was not detected on their hands because it was greater than 4 hours from the shooting to the sampling. Perhaps they washed their hands, or really were wearing gloves during the shooting, or maybe they used a long rifle or a shotgun where the GSR was not deposited on the hands. And so that's what we have for the gunshot residue, and you can see there's quite a bit of chemistry involved and some really nice instruments if you're able to work in one of those central labs that does GSR analysis. You get to use the scanning electron microscope and the energy dispersive detection for elemental analysis. So we'll see you next time.